I'm Nick Danforth,
I'm William Fiorentino.
I'm Sarah Mackenzie.
And I'm Rhea Nair.
and we did reduction of nitrous oxide emissions from coke ovens. So, coke ovens are a chamber of heat-resistant material that is used to burn the impurities out of extracted coal. The coal is then heated to separate coal gas, coal, water, and tar. The coal gas and coal water fuse together with carbon and the remaining ash, forming a hard residue, which is a more efficient fuel called coke. This process called coking reduces the weight of the coal by about half, making it more efficient to transport. And coke is used in blast furnaces to convert iron ore to iron and as a fuel source. Nitrous oxide emissions are the nitric oxide and nitrogen dioxide gas emissions, which are produced when nitrogen and oxygen interact at high temperatures, such as combustion, and are one of the most toxic air pollutants and also a main constituent in the formation of ground level ozone. Why control technology? Control technology is used to reduce the emissions of nitrous oxide particles, and the impact of nitrous oxide particles in the atmosphere include respiratory problems, eutrophication, acid rain, decreased visibility, formation of ground level ozone, and increased greenhouse gases. Coke oven operators have statistically significant excess mortality from respiratory tract, kidney, and prostate cancers as well. Some potential stakeholders include coke oven operators, iron or steel manufacturers, coal suppliers, business owners, and nearby residents in the environment.
So some considerations before we introduce our control technologies is that this is a facility that produces 18,000 tons of coal per day, and produces around 6.4 million cubic meters of waste gas per day. The NOx emission factor for this process is 0.013 kilograms of NOx emitted per megagram of coal processed. And we will be designing a control solution that reduces the NOx emissions by 75%. And for this, we're assuming a 700 to 750 Fahrenheit. So one of the first potential control technologies we're looking at is a low NOx burner. This burner controls the combustion process to produce lower flame temperatures, and lower flame temperatures reduces NOx formation. So this controls NOx prior to its creation. Another potential control technology is the selective catalytic reduction reactor. This is a post-combustion method that injects a reagent like urea or ammonia into the flue gas stream before it goes into the catalytic converter. The NOx is converted to nitrogen and water. Another potential control technology is a flue gas recirculation. This is when exhaust gas is recirculated back into the combustion air to reduce flame temperature and oxygen concentration. This FGR dilutes the fuel air mix with inert gases like nitrogen, water, and CO2 prior to it entering the burner or cylinder. And this produces less thermal NOx as this mixture of gases lowers the flame temperature. So the control technology that we selected is the selective catalytic reduction reactor. This method reduces NOx by 90 to 95% in some cases, which is well above the 75% reduction goal. And this technology could be employed by on its own, and it is as compared to the other two, which would be supplemented with other techniques or technologies. Some theoretical and design equations to consider are the volumetric flow rate for flue gas, which can be seen in the equation on top. Another one is the area of the catalyst, which uses the volumetric flow rate of the flue gas in its equation. Another one is the removal efficiency for NOx, and then also the volume of the catalyst, which uses all three of the equations as seen before.
So, with our initial calculations, we set many of the parameters used in our problem. Based on the 18,000 tons of coal per day produced, we set this to 18,000 megagrams per day. Based on the NOx emission factor of 0.13 kilograms of nitrogen oxide per megagram of coal produced, we calculated that 234 kilograms of nitrous oxide would be emitted per day. As the mass per volume was 234,000 grams per 6.4 times 10 to the 6 power cubic meters, we determined that the mass per volume would be converted to 36.56 milligrams per cubic meter. And since that we're looking to reduce emissions by 75%, the 234 kilograms was converted to 58.5 kilograms nitrous oxide emitted per day. And from 33.17 milligrams per cubic meter, we determined that there would be 9.14 milligrams per cubic meter at the outlet. So our problem statement is as such. A coke oven battery is used to produce coal into coke, which is used in manufacturing iron and steel. Consider a facility that produces 18,000 tons of coal per day, producing 6.4 times 10 to the 6 power cubic meters of waste gas per day. The nitrous oxide emission factor of this process is 0.013 kilograms of nitrous oxide emitted per megagram of coke produced. And our task was to design a control solution to reduce the nitrous oxide emissions by 75%. In the first part of our equation, we set the stoichiometric conversion of urea decomposition and the reduction of nitrogen dioxide and nitrogen dioxide. These are equations 1 and 2. So in the first equation, the urea and water are sent into the reaction chamber, where at a high heat and pressure, they're decomposed into ammonia and carbon dioxide. The reduction of nitrogen monoxide and nitrogen dioxide is that these unstable gases react with the ammonia and they then become nitrogen gas and water. And the assumption that we make in our equation is that of the nitrogen oxide emissions, 90% will be nitrogen monoxide and 10% will be nitrogen dioxide. In the second part of the equations, we calculated the daily nitrogen oxide emissions. So we did this by multiplying tons of coal produced per day, 18,000, by the emissions factor of 0.013 kilograms of nitrogen oxide per megagram of coal produced. And we multiplied this by 75% to calculate the 75% reduction factor that needed to be removed from the emissions. From this, we determined that 175.5 kilograms of nitrogen oxide per day would be removed. In the third part of our equation, we calculated the moles of nitrogen monoxide and nitrogen dioxide. We did this by multiplying the overall mass of nitrogen oxide, 175.5 kilograms, by the ratios of each gas that would be within the largest sample. And then we divided each one by the molar weight of that compound, 30.01 grams for nitrogen monoxide and 46.01 grams for nitrogen dioxide. From this, we determined that there would be 526.32 moles of nitrogen oxide and 38.11 moles of nitrogen dioxide.
And then after that, we took those mole values and added them together. And we used ammonia as our reactant. So in this case, we took the stoichiometric relationship of 2 moles of ammonia react with 1 mole of NOx, and that gave us 1,128 moles of ammonia that we would need in this case. And since we had the moles of ammonia, we took its molar mass and we found that we would need 15,815 grams of ammonia in this case to be able to react with the NOx that we have. So this slide is pretty much showing the rest of the reduction and sizing calculations that we did. So that very top equation is the equation for NOx removal efficiency. And so in this case, we knew that we wanted our removal efficiency to be 75%. So that was put in for removal efficiency, and we had 234 kilograms per day that we calculated prior. And at this point, we didn't know what our NOx out was going to be. So it ended up being calculated as 58.5 kilograms per day NOx out of the reactor, which did line up with our preliminary calculations. And after that, we did a gas hourly space volume calculation. But first, we had to choose that value is going to be 3,000 1/hours. And that was because this is a value that typically ranges between 1,000 and 5,000. So we thought 3,000 was good for a typical value for an industrial selective reactor. So in that case, we took that and used it for our residence time equation, which is the tau equals 3,600 divided by GHSV. And that gave us a residence time of 1.2 seconds. And after that, we found in the literature that this sort of reaction between the NOx and the ammonia and a catalyst is a first order decay. Even though it is a little bit more complicated than that, we can use that as a simplified version. So in this case, we have C out and C in, and we do have a residence time. So our goal here was just to get a calculated K and then check in the literature if that did line up with ammonia reactant paired with some sort of catalyst. So we did end up getting a K of 1.151/seconds. So that did line up with ammonia reactant paired with a titanium oxide catalyst. And so then we decided to find the volume of the catalyst that we would need for that. And so that was the gas flow from our Q given in the problem statement divided by GHSV. And so that gave us 89 cubic meters needed for that catalyst. And then we also decided to do the volume of the reactor in general, the reactor space, which was the residence time times the Q. So here you can see us converting the Q into a usable meters cubed per second and multiplying that by our 1/2 residence time, and also finding a reactor volume of 89 meters cubed. And then lastly, we have some other unique aspects of this problem. So first off, our fuel source. Different types and grades of fuel will affect SCR reactor size, and fuels with high heating value have higher gas flow rates, leading to larger SCRs. And in this case, other emissions from a Coke battery are often overlooked. We have polycyclic organic matter, benzenes, and other carcinogens that would have to be overlooked in this case. And there are two different types of coke ovens. The first one would be a beehive, which is a round structure with a spherical top that looks like a beehive, and it has an opening in the top and various small openings for draft at the base. And then there's also byproduct ovens, which are a rectangular structure with the front and back removable. and they are arranged so that all volatile byproducts can be pumped out. So those are all just other things to consider with this complicated problem statement. And these are the references that we had. So thank you everybody for watching.